second law of thermodynamics. Right? So, the second law of thermodynamics. The first law of thermodynamics basically said that energy is conserved. Energy is neither created nor destroyed. It's simply transferred from one place in the universe to another in the form of heat. So, basically what the first law says is you can't win. Okay? You can't make energy out of nothing. The second law of thermodynamics deals with the conversion of heat into work. Work is what we might call a high quality type of energy because it's something that you can use to do useful things like moving something requires work. Okay, heat would be what we would call a low quality of energy. All right. So anyway, if you want to convert heat into work, there's a limit to how much you can convert heat into work if you want to do it repeatedly. Okay. Now, first law of thermodynamics says if you've got 5 joules of heat, you can transfer 5 joules of heat. You can convert that to 5 joules worth of work, no problem. Okay, but second law says if you want to do it in a repeating manner, there's a limit to how much you can convert heat into work. And so the basic idea in the second law is you can't break even. Okay. First law says you can't win. The second law says you can't even break even. So, the second law of thermodynamics was based on studies of heat engines because the idea behind a heat engine is this. A heat engine is just a device that goes through a cyclic process. So every time it goes through a cycle, okay, it takes heat in from a hot reservoir, the hot surroundings, and as it goes through that cycle, it does work. So you're generating energy in the form of work as the engine goes through a cycle. So like as your car engine, in your car, your engine goes through a cycle. There's a piston that goes up and down, up and down. As that engine goes through a cycle, your car moves. Okay? So that's the work that the engine is doing. So in order for the engine to do that, it draws energy from something hot, okay, in the form of heat. But in the process of doing work, it has to put out heat back to a colder surroundings. In your car, what would that colder surroundings be? The cold reservoir. That's your radiator. Okay? I don't know anything about cars. Okay.
It's like someone saying.
You have a radiator in your car that you feel with coolant. Antifreeze, anti-boil. Okay. So that when I was growing up, where I come from, it's just what we just put water in there because water is, if you remember, has a very high heat capacity, very high specific heat, so it absorbs a lot of energy without raising its temperature too much. And what I remember as a kid is sometimes we drive the truck so far that the water would overheat and the radiator it would just, yeah.
Is that why people like to go to air intake systems into their vehicles?
A cold air intake system.
Yeah, like you just make what you like the cold air put out more, and like gives the engine more power.
Probably, if it's something that draws, something that allows you. Your radiator is in front of your engine block, so basically that's what it does. It draws heat away from your engine. Okay. So anyway, your engine goes through a cyclic process over and over again. Okay, so delta U every time it goes through a cycle is 0. We've already established that. Internal energy change for a cyclic process is 0. Delta U is 0. So it draws heat from the hot reservoir. So Q input here would be a positive value, right? Q in is positive. And then it converts heat into work. So our W out here is going to be a negative number. Okay? And it dumps some of that heat energy that it took from the hot surroundings into colder surroundings. So Q out over here is going to be a negative number. Now the efficiency of your heat engine is equal to negative W out over Q in. So it's the ratio of how much it's a ratio of how much work was put out compared to how much heat was taken in. So if everything, all the heat input was converted into work, then you have 100% efficiency. And second law basically says you can't be 100% efficient. Okay. Now, why is there a negative sign there? Because we want our efficiency sheet to be just a positive number. W out, if you notice, is a negative number. So efficiency is negative W out over Q in. Okay, so that's what heat engine does. So here's the second law. Based on studies of heat engine, the Kelvin-Planck statement of second law is this. It says that for a cyclic process, okay, for a cyclic process, okay, a cyclic process is impossible if the sole outcome is a complete conversion of heat into work. Just what I said earlier, right? So if you have a cyclic process, you cannot have 100% efficiency. So efficiency of your heat engine in this case would be less than 1. Right? Now you can also state the second law in terms of what's known as the Clausius statement. The Clausius statement basically says a cyclic process is impossible if the sole outcome is a transfer of heat from a cold reservoir to a hot reservoir. Okay, so in other words, what if you have a process that goes through cycles, but it draws heat in from the cold reservoir? Let's say it takes in 5 joules from the cold reservoir. The first law of thermodynamics says it should dump, for the whole cyclic process, delta U is 0, so it should dump how much energy out? Also 5 joules, right? So Q in is negative 5, Q out would be plus 5. So if you take 5 joules out of the inside of your refrigerator should dump 5 joules out to the room, to the kitchen, right? Now, the first law of thermodynamics has no problem with that. As long as you took 5 and you give back 5, the first law has no problem with it. But the second law says, no, it can't happen. Energy will not flow spontaneously from something cold to something hot. Okay, you cannot operate a refrigerator without paying energy. You have to do electrical work. You have to have work input for that process to happen. Heat, we know, naturally goes from something hot to something cold. So this statement basically says it's not possible for heat to just go from something cold to something hot without any external assistance. Okay, that's the second law of thermodynamics. That's another way of stating the second law of thermodynamics. And you can prove that those two statements are in fact equivalent, but we're not going to go into that. We'll reserve that for a class in grad school. All right, so limits on efficiency. Maximum efficiency of a heat engine between two temperatures, T hot and T cold, is limited by the second law to T hot minus T cold over T hot. Okay, and what is the maximum efficiency of an engine operating between 25 degrees and 100 degrees Celsius? So how would we calculate your efficiency here? T hot would be what? (100), which is 373 Kelvin, right? Minus T cold would be 298 Kelvin over T hot, which is 373 Kelvin. Right? So you can see that that's going to be 1 minus 298 over 373. What's 298 over 373? So this is your maximum efficiency. So 1 minus 0.7989. So our efficiency is how much? 0.2011. So that's your maximum efficiency. Okay? That's just, you can show that, like I said, we're not going to go into deriving that, okay? But that's your maximum efficiency. But that's not achievable. You can show that that is in fact the case. You get maximum efficiency if you're using a reversible process. You remember what reversible process was? something, it's an imaginary process that you carry out through a series of infinitesimally small steps. So that's really an impossible process. So this is the upper limit to the efficiency of an engine operating between two temperatures. Okay, you can illustrate this using what's known as the Carnot cycle. Okay, here's an example. This is a reversible process involving an ideal gas. And in a Carnot cycle, what you do is this. Yeah. You start with an initial state, P1, V1, T1, right? So point number 1. You imagine a reversible isothermal process, expanded, to point number 2. So this is going to be P2, V2, same temperature, T1. So step 1 is let's call this step A. Okay. Is a reversible isothermal process, reversible isothermal expansion. Right. Now, let's imagine what's happening here. Your gas is expanding, so it's doing work, right? So it's putting out work. So W here is negative, right? We know what the formula is for that work. What is it? So for process A, what's our work? You remember? nRT ln V2 over V1. Remember, work is negative integral of PdV for a reversible expansion of an ideal gas, and P is nRT over V, right? So this is nRT1 ln V2 over V1. That's a negative number because V2 is large. Oh, negative nRT, right? That's a negative number. Your system is going to be doing work. And for an ideal gas, delta U is 0 for isothermal expansion, so Q will just be negative WA, right? So all the heat input is now being put out as work, right? But you have to go back to P1, V1, T1, and that's where you will have eventually end up having to dump heat back into the surroundings in order to be able to go back to your initial state. So step B, second step, we're going to do, okay, an adiabatic process. So second step, we're going to do a reversible adiabatic process. And so when your gas is expanding adiabatically, it's still doing work, but you're not replenishing, you're not allowing heat to come in. So you expect your gas to cool down, right? It's doing work, losing energy, but no heat can come in, so the temperature of your gas is going to drop. So you're going to be crossing into a different isotherm. So let's call this second final point right here. Let's call this point number 3 is P3, okay? That's a different pressure, right? And that's going to be V3, T3. Okay. How is P2, V2, T1 and P3, V3, T3 related? What's the equation for an adiabat, a reversible adiabat? So we're going to call this process B. For B, what do we know about B? Q for B is what? 0, right? And delta U for this is just equal to CV delta T, so it's just going to be equal to W for step B. Now you could have done W equals minus integral of PdV. You could do that if you, but this is a lot quicker. Just since we know that Q is equal to 0, then delta U is just W, right? Now, how do we get, what's the relationship between P2, V2, T1 and P3, V3, T3? Remember, for a reversible adiabat, PV to the gamma is a constant, right? or you can say nRT over V times V to the gamma is a constant. So you can also say that T V to the gamma minus 1 equals T, a constant. If that is the case, or you can say, let me rewrite this into something easier for me to remember. T over V raised to the power 1 minus gamma. Okay. 1 minus gamma is a negative. I'm just going to keep it like that. TV, is that correct? Gamma minus 1, and that's T. So this thing is a constant, right? If you remember this, gamma, what was gamma? Gamma is Cp over Cv. Okay, that's a number larger than 1. So, what can we do? What do we know about the relationship then between T1, V2, and V3, T3? So we can say that T1 V2 to the gamma minus 1 equals T3 V3 to the gamma minus 1. Okay? Where am I headed with this one? We'll see later. Okay. Now, once you've done that, okay, you let this time you go back isothermally, okay, to some point here, which we're going to call point number 4. In this process, step C, okay, you're going to do a reversible isothermal compression. Back to point number 4, so that you can go back from point number 4 back to point number 1 again using an, so this is going to be process D, using an ADEB, so let's call this P4 V4 T3, okay? So T1 is T hot, right? And T3 is T cold. Got that? Okay. So process D would be another reversible adiabatic. Reversible adiabatic process. So that's a Carnot cycle. So what happens? In process A, you absorb heat, you do work. Okay? Process B, you continue doing work, but you don't absorb any more heat. In process C, so your system cools down. Okay? In process C, what happens? You're compressing. So this time you're doing work on the system, right? So system is doing work, and Q would be what? Negative. The system will now be dumping heat back to the surroundings. Okay? And then you continue doing work to your system to bring it back to the original state. So this is a Carnot cycle. You have a series of isotherm, adiabat, isotherm, adiabat. So the area inside this region right here, that's the net amount of work that you put out. Okay? So the area in between these 4 curves, that's the amount of heat. Remember, integral of PdV, the area under a curve is just work, right? So that's the net work done there. So that's the shaded area. That's your net work. So you can see that's going to be, the output is greater than the input work. Okay, so the area under this curve, this first curve, process A, is greater than the area under process C. So that's going to be a negative number. So the net effect of this cycle is you're drawing heat from a hot reservoir, you're dumping heat to a cold reservoir. You're dumping heat to a cold reservoir. In the process, you're doing work. Okay? So, Anyway, let's make this your assignment. Figure out the total work done. Okay? So net work. So you're going to have to figure out these relationships between P1, V1, T1, P2, V2, T2, T1, P3, V3, T3, and P4, V4, T4. Okay? And verify that the efficiency of a Carnot cycle would just be equal to what we said earlier, okay, which is what? T hot minus T cold over T hot. So efficiency is equal to what? Negative W out over Qn. What is Qn in this case? Qn will be Qa, right? Process A is the only process here where you're drawing heat from the surroundings. So it's going to be Qa. And what is W out? That's just the area under that curve, right? So W out is just the total W. Okay? That would be your efficiency. So W out would be that total area inside those four curves. That would be your next homework. All right. So, in a reversible engine, delta U we said is equal to 0. So Q in plus W out plus Q out is equal to 0. Okay. And so we can rearrange this, and what do we get? If we solve for efficiency. Efficiency is negative W out over Q in. So then you can say that that's what equal to what? Solve for W out here, what do we get? W out is equal to Q negative of Q in plus Q out, correct? W out equals negative Q in plus Q out. So negative W out is just Q in plus Q out. And so efficiency is just Q in plus Q out over Q in. Okay? So that's your formula for efficiency. Right? In terms of Q's and W's. This W out, that's just the net total of all the work for the entire cycle. Okay? And W out, we know is going to be a negative number. Now, if your cycle is reversible, like I said, you get maximum efficiency. And as you will show with your, as you can show with your, what do you call this, Carnot cycle, you can show that this is equal to T hot minus T cold over T hot. Okay, so from these two equations right here, okay, you'd be able to show that Qn over T hot plus Q out over T cold is going to be equal to 0. Okay, let's do that. Let's say that you have Qn plus Q out over Qn is equal to T hot minus T cold over T hot. Right? Let's simplify this. Let's rewrite this as 1 minus Q out over Qn. Okay, Qn over Qn is 1. Okay. Oh, that should be plus, right? Equals T hot over T hot is 1 minus T cold over T hot. And so we can cancel the 1 from both sides. What can you say? What can you show here? Q out over Q in equals 1. Negative T cold over T hot. And let's rearrange this. So I can put Okay, Qn happened when the system was in contact with the hot reservoir, right? So I'm going to rearrange this. I'm going to say Q out over T cold equals negative Qn over T hot. You're still following that one? I'm just switching these two. Divide both sides by T cold, multiply both sides by Qn. And then I'm going to move everything to the left. I'm going to show that Q out over T cold plus Qn over T hot is equal to 0. So, in other words, the sum of Q over T would be equal to 0 for this reversible process. Okay? So, what's the point of showing this? It's very important. This is a very important result that you can show from the Carnot cycle. You can use the Carnot cycle as an example. But this is going to be true for any reversible process happening between two temperatures. What basically that says is that you can in fact use that to prove, okay, that integral of dq over t, remember, integral of dq over t is just, for a Carnot cycle would have been what? Would just be Q hot over T hot plus Q cold. That will be Q out over T cold. Okay? Now that's going to be equal to 0. Okay? So this integral right here, you'll notice this circle around the integral, that means a cyclic integral. You go from the same initial state to the same final state. A cyclic process. The integral of dq over t is equal to 0. This is if the process happens to be reversible. What's the point of this? The significance of this result is that if you were to take any reversible path, okay, the integral of dq over t must be the same. Okay? If you remember, integral of du over a cyclic process, what's delta u for a cyclic process? 0, right? So if the integral of dq over t for a cyclic process, provided it's reversible, is equal to 0, okay, then that suggests that dq over t is a differential element for some state function, some property of the system that depends only on the state. Okay, so the integral of dq over t is the same for any reversible path that you take, as long as you have the same initial and final state. So we can then say that if we can imagine a reversible path going from one state to another, okay, the integral of dq over t for each step in that path would be equal to the differential of some state function, which we're going to call entropy. So this is the basis then for defining entropy. We say that entropy, okay, is something that whose change we can calculate by integrating dq over t. So we can calculate delta S. If your system goes from one state to another, we can calculate delta S by integrating dq over t if we imagine a reversible path going from that initial state to that final state. It doesn't matter how it actually happened. All we have to know is what's the initial state, what's the final state, and then we imagine any reversible path that goes from the initial state to the final state, regardless of what that path is. It will always give you the same answer for the integral of dq over t, provided that path you imagine is reversible. Okay, so this really gives us the defining equation for entropy. This is how we will calculate the change in entropy for a system undergoing a change. Identify the initial state, identify the final state. Doesn't matter how you got from the initial state to your final state. Just imagine a way to get there reversibly and integrate dq over t over that reversible path. Okay? So, here it is. If you want to calculate entropy changes, okay, delta S, imagine a reversible path from your initial state to the final state. Integrate dq over t for the path you imagine. What if the process is not reversible? Doesn't matter. You're just imagining it anyway. Doesn't matter how it actually happened. Okay? The delta S you get, regardless of which imaginary path you take, the delta S that you end up calculating is going to be the same. So that suggests that S is a state function. Right? So let's look at an example. So reversible heating at constant pressure, where there's no phase change or chemical change. How would you physically do reversible heating at constant pressure? So if I have a sample, I want to heat it at constant pressure, what would I do? I just leave it open to the atmosphere, so it will be at 1 atmosphere pressure. How do I get its temperature to rise reversibly? So if my sample's at 25 degrees Celsius, I want it to bring it to 30 degrees. What should I do? Do I stick it in an oven with 30 degrees? That would be an irreversible spontaneous process, right? So what would I do? I put it in an oven that's at exactly the same temperature as my system, right? 25 degrees. Crank up the temperature for the oven to what? 25.00000001. It's very slight difference. That's still not reversible, but that's as close as you can get. That's an approximation, right? And then raise the temperature a little bit more, and a little bit more, and a little bit more. And so that would be your reversible heating. Okay, so dq is Cp dt, if you remember, right? What is Cp? Heat capacity at constant pressure. So what's our ds? It's just going to be dq, which is Cp over t, right? Look at this. From this one, you can say that's dq is Cp dt. Oops, sorry. dq, which is Cp dt over t. Right? So if your heat capacity happens to be independent of temperature, and you can make this assumption when you're looking at a temperature interval that's small enough, like a few degrees, right? Then you just integrate. If you integrate Cp dt over t, what do you get? You can pull out Cp from your integral. So that's Cp integral of dt over t. What's integral of dt over t? Integral of dt over t is ln of t. So this becomes Cp ln t final over t initial. Okay? So that's how you would get delta S if you're heating something at constant pressure. What if temperature, your Cp does depend on temperature? What would you have to do? Let's look at an example. Let's say we have, let's say oxygen. And let's see if I can get the Cp for oxygen. Let's go to the web book. .inst.gov, formula. Let's do O2, gas phase, thermodynamics data. Okay, here's your Cp for oxygen. Okay, here's the formula. And where's your A, B, C, and D? Right here. The values for your constants are over here. Okay, so you look it up. So it's a function of temperature. And this T right here is given in what? In Kelvin. Okay, temperature in Kelvin. But this T is actually over 1,000. But so it's a polynomial for. Let's see, what is it? So you can see it's A plus BT plus CT squared plus DT cubed plus E over T squared. Okay? And you have your A, B, C, D, and E. You can look those up. You can just plug in the numbers. This is from 100 to 700 Kelvin. And this is 700 Kelvin to 2000 Kelvin. And that's 2000 Kelvin to 600 Kelvin. So what would I have to do? I would just have to go what? Delta S is equal to integral of AT plus BT squared plus CT cubed plus D. How was it? I'm sorry. A plus BT. So it's A plus BT squared plus bt plus ct squared plus dt cubed plus e over t squared dt. And then dt, that's cp over t, so you have to divide by t, okay? You go from t1 to t2. So how would I integrate this? What's the integral of a over t dt? That's going to be 1. So that's integral of a dt over t plus integral of bt dt over t plus integral of ct squared dt over t. Oops. Plus and so on. What's this first term equal to? This is a ln t2 over t1, right? You're evaluating from t1 to t2. What's the second term equal to? B delta t, right? B t2 minus t1. What is this third term equal to? What's the integral of ct squared over t? C over 2 t2 squared minus t1 squared. You can see where that comes from? Okay. Integral of ct dt over ct squared dt over t is equal to integral of ct dt, so that's c times t squared over 2. Okay. What's the last term? Oh, the next term would be what? dt cubed dt over t would be what? d over 3 t2 cubed minus t1 cubed. All right. And the last one, what's the integral of e over t squared dt over t? What would that be? That's the last one, right? E over t squared. So that's e over t cubed dt. What would that be? E t to the negative 3 plus 1 over negative 3 plus 1, right? Evaluated from t1 to t2. So that gives us, so the last term is going to be e t to the negative 2 over negative 2. So that's evaluated from t1 to t2. So that last term is going to be negative e over 2 1 over t2 squared minus 1 over t1 squared. Okay, so that's how you would calculate your integral. Okay. Let's do a quick calculation of that on MathCAD. So you would say integral, what was it? A times A plus T, B times T, right? Plus C times T squared plus D times T cubed plus E over T squared dt from T1 to T2. Let me see if I can evaluate this. And there it is. That's the entire expression right there. Okay, so evaluated at T2 minus the integral evaluated at T1. So it makes things a lot easier. Okay, moving on. What about an isobaric heating or cooling? Okay, this is the same thing. So here's an example. What's the entropy change when 0.28 moles of ideal monatomic gas undergoes isobaric heating from 200 Kelvin to 300 Kelvin? Since we're not given the actual gas, we can't look it up. We just have to estimate it based on what we know. What do we know about ideal monatomic gas? CV is 3/2 NR, right? And CP would be CV plus N plus R, NR, right? So that's going to be 5/2 NR. So what's our delta S then? Integral of Cp dt over T. So integral of 5/2 NR dt over T from 200 Kelvin to 300 Kelvin. Okay, so we're integrating from 200 Kelvin to 300 Kelvin. So what would this be? That's just Cp is a constant, so we can actually just factor that out. So that's Cp ln T2 over T1, so that's going to be what? Cp is 5/2 NR, ln of T2 is 300 Kelvin over T1, which is 200 Kelvin. Kelvin cancels out. What's that number? Five halves times N is 0.28 moles. R is 8.314 joules per mole per Kelvin. And natural log of 300 over 200 is what? 1.5. So what's the final answer? You should get 2.36 joules per Kelvin. See if you get that. What was that? 5/2 times NR. So 5 over 2 times N, which is 0.28, times R is 8.314, ln of 300 over 200. That gives me 2.36. Okay. So that's 2.36, and the unit is, moles cancel out, the unit for entropy is joules per Kelvin. Why joules per Kelvin? Remember the formula for entropy is dQ over T. What's the unit for Q? Joules. The unit for temperature is Kelvin. So the unit for entropy is joules per Kelvin. What about an isocoric heating or cooling? Well, dQ in this case is CV dt, right? Constant volume. So dQ over T is CV dt over T. So again, okay, this is the general formula right here. Integral of dQ over T in this case is CV dt over T. If you're dealing with a small interval, temperature interval, you can assume your temperature is more or less, your CV is more or less independent of temperature, so you can factor that out of your integral. So that's going to be CV ln dt over T, which will be CV ln T final over T initial. Okay. So what would it be if you have 0.15 moles of CO2 and undergoes isocoric heating from 300 Kelvin to 500 Kelvin? If you assume it's ideal in a rigid rotor, what's our CV? CO2. CV is 3/2 NR plus, okay, let's do this per mole first. So N times CV per mole is 3/2 NR, 3/2 R. Why 3/2 R? Where does this come from? We have 3 translational modes, right? And what's the other contribution to CV? It's a linear molecule, so it's 1/2 R for each rotational mode. So linear molecule. How many rotational modes for a linear molecule? 2. So plus 2/2 R. Okay. So our CV is that. So what's our CP, if this was ideal, would be CV plus NR, right? So our CV is how much? It's going to be 5/2 NR. Okay, so if you have 0.15 moles of CO2, it undergoes isocoric heating from 300 to 500 Kelvin. What would be our delta S? Delta S would be integral of NCV dt, which is going to be NCV ln T2 over T1. So that will just be equal to, okay, it's just CV dt, sorry. Just CV dt. It's N times CV per mole, or just CV, okay. So this is going to be 5/2 NR ln, going from what temperature to what temperature? 300 to 500. So that's 500 over 300. Okay. So that gives us how much? 5/2. And how many moles do we have here? 0.15 moles. That's our R. 8.314 joules per Kelvin per mole. And you have ln of 5 over 3, 500 over 300. So that gives us, okay, 5/2 times number of moles is 0.15 times 8.314 times ln of 500 over 300 equals 1.593. Okay. So 1.6 joules per Kelvin. Moles cancel out, so the unit is joules per Kelvin. Okay, 1.6 joules per Kelvin is your delta S. Okay, what about isothermal phase changes? Well, let's look at the phase change that's isothermal and constant pressure at the same time. So this would be like a phase change, okay? Phase change at constant temperature and pressure. So for example, your water vaporizing at 100 degrees Celsius under a constant atmospheric pressure, or your ice melting at 0 degrees Celsius at constant temperature and pressure. Constant temperature being the melting point of the ice, temperature, constant pressure being atmospheric pressure. Then if you remember, we said dq is just equal to dh, right? Q is equal to delta H at constant pressure. So dq will just be dH over T. But if we're having temperature constant as well, it's isothermal, What's the integral of dH over T? If temperature is constant, I can factor out, dH over T. If your temperature is constant, I can move that temperature out of my integral. What's the integral of dH? It's just delta H. Okay? So delta S would be delta H over T. Now, if instead we're doing it at constant volume, dQ at constant volume is equal to delta U at du at constant volume, right? So delta S in this case, ds would be dQ over T, would be du over T at constant volume. And so if you integrate this, you can factor out T if it's isothermal as well. And delta S will just be delta U over T. Okay? So if we're looking at phase changes, no chemical change involved, you can do it at constant pressure or constant volume, then those would be your formulas for delta S. So here's an example. Constant pressure of 1 bar, 5.60 kilojoules was needed to melt a solid at 350 degrees Kelvin, 350 Kelvin. What is delta H and delta S? What's our delta H? It's just Q at constant pressure, right? So delta H at constant pressure is Q at constant pressure, and what is it? 5.6, positive, right? Why positive? Melting is endothermic, right? So that's the heat of fusion at constant pressure. What is delta S? This is isothermal, isobaric. It's just Q over T, right? This is just delta H over T, since this is at constant pressure. And what would it be? Positive 5.60 times 10 to the third joules divided by the temperature in Kelvin, which is 350 Kelvin. And that gives you 5.6 times 10 to the third divided by 350, 16. Okay. So, that is 16 joules per Kelvin. 16.0 joules per Kelvin. That's your delta S. That's your delta H and your delta S. Okay. Now, there's a rule, there's an empirical known as Trouton's rule. This is a very useful rule for estimating delta S for vaporization at the boiling point. Okay, delta S vaporization at the boiling point is around 88 joules per Kelvin. Okay, this is an empirical rule. Yes, it is. Okay. All right, so we'll just continue this next time. Oops.